the most powerful telescope humanity has ever built, just made a discovery that could change everything we know about life in the universe. The James Webb, floating 1.5 million kilometers from Earth, found a distant planet with something incredible: 96.8% chance of having life. Imagine a world completely different from ours, perhaps with oceans of colors we've never seen, skies with 2 or 3 stars shining at the same time, and who knows, creatures that evolved in ways we can't even imagine. For years, scientists searched for signs of life beyond Earth, scanning thousands of planets without success. But now, with Webb's golden eyes looking into deep space, we've finally found an almost perfect candidate. What would it be like to wake up on a planet where gravity is different, where days last longer than our years, where the very chemistry of life may have taken completely new paths? Are we about to discover that we were never alone in this infinite universe? Subscribe to the channel, leave your like and comment from what part of the world you're watching, get comfortable and relax. Let's begin. What if I told you there's a set of golden mirrors, shaped like a giant sunflower, quietly floating way out in space, and it might be holding the answers to some of humanity's oldest mysteries? This isn't a scene from a movie. That golden sunflower is called the James Webb Space Telescope, and it's not just an expensive gadget. It's one of the biggest scientific leaps humans have made in trying to understand where we come from and if we're truly alone out there. For decades, people have wondered about life on other planets, distant corners of the universe, and how everything even got its start. A lot of hope and imagination went into Earth's biggest telescopes, but the James Webb was designed from scratch to push past everything that limited our view before. To really get how big a deal this telescope is, you have to picture exactly where it is. It's not just hanging out above Earth's atmosphere like the Hubble. Instead, it's sitting at the so-called second Lagrange point, which is more than 1,500,000 kilometers from us. That's 4 times farther than the Moon, and there's a reason the Webb team picked such a wild and lonely location. Out there, Earth's heat and glow don't mess things up, and the telescope can cool down enough to pick up the faintest traces of light. This spot is like the universe's best front row seat that keeps the distractions of our home planet firmly out of the way. Most people know that the James Webb Space Telescope is, in technical terms, a far more advanced version of the old Hubble telescope. But what really sets Webb apart is its ability to see in the infrared. That's a big deal because almost everything in the universe, from ancient galaxies to newborn stars and even mysterious exoplanets, gives off heat, infrared light that older telescopes just couldn't see. When regular telescopes look off into space, they can get blocked or blinded by dust clouds and other stuff floating out there, but the James Webb sees right through that, showing us parts of the cosmos that have never been visible before. It's kind of like having night vision goggles turned up to maximum. Now, when you're talking about peering into deep space, you might wonder what the telescope is actually looking for. Sure, it gives us pretty images of far-off galaxies, but the real treasure is in the details it uncovers, the history of our universe, how galaxies form, how stars are born, and most excitingly, how planets take shape around those stars. That's why so much of the mission is dedicated to finding and studying exoplanets. Those are planets outside our own solar system, orbiting stars that are sometimes hundreds or even thousands of light years away. The ultimate goal isn't just to spot them, but to figure out what their atmospheres are made of and see if there's even a slight chance life could exist there. If you try to picture the telescope itself, imagine a honeycomb of 18 gold-covered mirrors, each shaped in a hexagon and pieced together to make one massive, light-catching surface. These mirrors collect the faintest little bits of light that have travelled across unimaginable distances. Light so old and dim you wouldn't even know it was there without incredibly sensitive equipment. To make sure nothing interferes with these delicate measurements, the telescope has a sun shield about the size of a tennis court that always faces away from the sun, keeping everything super cold. The colder you can get these sensors, the better they work at picking up those distant, ancient signals. But just building the telescope wasn't enough. Everything about getting it ready and launching it was complicated in the extreme. Each mirror section is made of beryllium, a super-light metal and covered with a thin layer of real gold, because gold is incredibly good at reflecting infrared light. While launching, the whole thing was folded up, almost like origami, inside a rocket, and then carefully unfolded itself on its way out to that lonely spot in space. There was no room for mistakes. Fixing problems at that distance is impossible. The engineering behind just this folding and deploying process still blows even seasoned scientists away. As soon as the James Webb turned its eyes skyward and started sending back data, everyone realized how powerful it really was. Not only could it look at galaxies more than 13 billion years old, back to when the universe was just a baby, it could also focus on tiny points of light and tell us what those points are made of. When it comes to searching for exoplanets, the telescope isn't looking for in-your-face signals or alien cities glowing in the night. Instead, scientists use it to catch the tiniest changes as a planet passes in front of its star. With its super-sensitive instruments, Webb picks up the faint starlight that passes through a planet's atmosphere and then splits that light into different colors, or wavelengths. By looking closely at which wavelengths get absorbed or passed through, scientists can tell exactly what kinds of gases are floating in that atmosphere. This kind of observation, called spectroscopy, offers us clues that have never been possible before. For example, the James Webb might spot things like water vapor, methane, or even oxygen in a planet's atmosphere, which could hint at the ingredients for life. These aren't just vague guesses. Scientists build detailed models and then compare what's seen by the telescope with what they would expect from both lifeless and life-bearing worlds. Those comparisons let them assign probabilities to the chances of life existing somewhere out there. Now, it's important to know that none of this would be possible without getting above Earth's own atmosphere, which blocks and distorts a ton of important signals. That's the big difference between telescopes stuck on the ground and telescopes we launch into space. Webb exists in an environment that lets it work with almost no interference. Every detail of its mission, from the orbit to the choice of mirror metal to the mind-blowing computing power on board, puts science in the driver's seat. What's even more amazing is that the telescope is so steady and so well positioned in its orbit that it can stare at a single target for hours, even days, building up a detailed picture of what's going on there. This is key for exoplanet hunting. The planets that might have life aren't blazing in brightness. They're so faint compared to their stars that it takes immense patience and technical skill to pick them out. Webb can measure the dip in starlight as a planet goes by, and then take that faint fingerprint and break it down to an unprecedented level of detail. Scientists use this flood of information to start answering some pretty big questions. What kind of planets are most common? How do solar systems form? Most importantly, are there other places out there that could possibly support life, or even already do? The Webb has totally changed the game by giving us clarity we just didn't have before. On top of this, James Webb's mission isn't just about finding planets. Its field of view also takes in the oldest stars and galaxies, helping us study everything from the chemistry of the first light in the universe to the evolution of the biggest cosmic structures. By understanding those ancient stars and newborn planets, we start seeing ourselves as part of a much bigger story. Sometimes the telescope's observations end up being completely surprising. It's already spotted stars coming together out of chaotic clouds of dust that no one expected. Patterns in distant galaxies are way more complex than old models predicted. All this brand new information doesn't just add to our stack of knowledge, it changes the basic questions scientists ask and even shifts what they hope to find on the next observation run. Since launch day, the telescope's most headline-grabbing role involves those exoplanet discoveries. With each round of data, researchers can refine their search, choosing planets that orbit in the so-called habitable zone, where temperatures are in a range where liquid water might exist. James Webb's infrared sensors let it see right through the bright glare of the host stars and pick up signs of water vapor, carbon dioxide, and other molecules that tend to show up when planets are friendly to life as we know it. The approach is careful. Instead of jumping to wild conclusions, scientists use every conceivable tool to rule out false positives, those situations where something in the environment or a weird geology could imitate the signs of life. Webb's ultra-precise measurements, checked by teams of experts all over the world, have raised confidence in results like never before. Suddenly, places that once seemed like long shots are starting to look like genuinely promising homes for life. When you take a step back, the whole story of the James Webb Space Telescope is a kind of slow-motion revolution. Every step, from picking out the tiniest materials for the mirrors to unfolding it in deep space to interpreting its streams of data, is done under the glare of hope and curiosity. Scientists from all over the planet, speaking every language you can imagine, team up on projects, share findings, and build a growing picture of a universe teeming with surprises. One of the most stunning achievements so far is the detection of a planet with a 96.8% probability of life by the Webb. This finding didn't come out of nowhere. It's the result of methodical searching, massive teamwork, and decades of building better and better technology. Even if some people are skeptical, and it's healthy to be cautious, the evidence keeps piling up that our universe might be friendlier to life than anyone imagined a century ago. But it's not all about the tech. As powerful as the telescope is, it's really a tool that extends our senses across what used to be impossible distances. Just the idea that human ingenuity can build something so precise, send it so far, and then use it to peer at alien atmospheres or ancient galaxies is a measure of what humans, working together for a common purpose, can actually achieve. And the story of the James Webb Space Telescope isn't finished. With each year, it keeps collecting jaw-dropping data, rewriting textbooks, and giving us a share of cosmic perspective that nothing else so far could offer. Whether it's helping us answer the big questions about life elsewhere, or giving us a new sense of our place in the story of everything, the Webb is a triumph that needed vision, teamwork, and a desire to look further than anyone had gone before. Standing on Earth and looking up at the night sky, it's now almost guaranteed that some of the light coming down has already been inspected, recorded, and analysed by this great golden telescope floating in the cold, silent dark far from home. What started as a dream to see further has turned into a steady stream of new questions, hopeful discoveries, and for the first time, a real possibility of knowing we're not alone. The James Webb Space Telescope is more than just an eye in the sky. It's humanity's best shot yet at finally seeing ourselves as part of a cosmic neighborhood and maybe, just maybe, making contact with something else out there, even if what that looks like is still up for us to discover. With all the new possibilities opening up, especially when it comes to tracking down signs of life on planets far beyond our solar system, people are naturally wondering how scientists can really know what's going on so far away. It's not like anybody is hopping onto a spacecraft and actually landing on these distant planets, at least not anytime soon. So, the practical question becomes, how does a telescope sitting out in space manage to tell us anything at all about what might be happening on a planet orbiting a star, say 100 or even 1,000 light years from Earth? This is where the work of the James Webb Space Telescope gets really interesting, because it's all about paying close attention to tiny changes in the way light travels through space. If you can figure out how to read those changes, you get some of the most valuable clues that exist for spotting the basic ingredients of life. Almost every step in the search for life starts with light. Think of stars shining and planets orbiting. As a planet passes in front of its star from our perspective, a little bit of that starlight passes through the upper layers of the planet's atmosphere before it gets to the telescope's mirrors. During this brief moment, something fascinating happens. The gases in the planet's atmosphere actually absorb certain colours or wavelengths of that starlight. When the James Webb Space Telescope collects and breaks down this light, it is possible to see those missing colours and match them with specific gases. That breakdown of light is called spectroscopy, and it is right at the heart of how scientists look for life across impossibly vast distances. Spectroscopy isn't new to astronomy, but the technology on the James Webb Space Telescope has taken this whole process to a much higher level of precision. Traditional telescopes worked mainly with light we can see. The Webb, by focusing on infrared light, is looking at a part of the spectrum that tells us a lot about temperatures, chemistry, and even the presence of what scientists call biosignature gases. These biosignatures are groups of molecules that, if found together in the right balances, really start raising eyebrows. Imagine detecting a mix of oxygen and methane together. Those two gases, if you find them hanging around in significant amounts, do not typically stay in balance on their own. Something has to keep replenishing them. On Earth, that something is life. So spotting that combination on another planet is a big deal, but it's not the only clue researchers are after. Whenever starlight travels through a planet's atmosphere, molecules like water vapor, carbon dioxide, methane, or ozone can leave clear, unique signatures. Each of these molecules blocks a little bit of light at a particular wavelength, as if they're building a barcode for that atmosphere. By comparing what the telescope sees when a planet is in front of its star and when it's not, researchers can subtract away the light from the star by itself and see what's left. What's left are those chemical fingerprints. This method is called transmission spectroscopy. Once you've got those barcodes, it's time for a careful detective process. Researchers compare what they find with thousands of simulated atmospheres created on supercomputers. Those models cover everything from dead rocky worlds to lush active biospheres. The closer the match between the planet's measured barcodes and the ones that life would produce, the more likely it is that something alive is changing the makeup of that atmosphere. The impressive thing about the James Webb Space Telescope is not just its sensitivity, but how steady and patient it can be. For planets that pass in front of their stars on regular schedules, the telescope can observe multiple transits, waiting for just the right moment to snag useful data. Strong signals are rare, so this process can take months or even years for just one likely planet. Webb can quickly tell if a world has a thick atmosphere or none at all, which saves a lot of time by ruling out the totally barren cases. If there is an atmosphere, especially one with a combination of water, methane, and oxygen, that is where scientists get excited. But excitement is always mixed with heavy skepticism, because nature has ways of faking some of these signals through volcanoes, wild lightning storms, or pure chemistry. To separate out these false alarms, scientists look deeper. They analyze how much of each gas is present and hunt for combinations that, on Earth at least, only stick around if something alive is working constantly to keep them there. For instance, oxygen likes to react with other chemicals and disappear unless plants, algae, or some other biology is pumping it back into the air. The same thing goes for methane. On a lot of dead worlds, methane can get created by geologic activity, but it quickly vanishes unless it is constantly renewed. That is why seeing both methane and oxygen together is such a major red flag for life. There aren't many natural processes that can keep them balanced without living things involved. Sometimes the shape of the planet's transit matters too. By using extra-sensitive instruments, Webb can measure subtle changes in the light curve, the way the brightness of the star changes as the planet goes by. Any dips or odd shapes in that curve can point to clouds, hazes, or even signs of rain in an atmosphere. This extra layer of information helps scientists figure out not just what gases are present, but how thick or energetic an atmosphere might be. On Earth, weather cycles keep our atmosphere moving and mixing. Seeing similar patterns on alien worlds adds points in favor of that planet being lively. Though again, nobody jumps to conclusions without carefully checking every possibility. The tools used by the Webb are incredibly precise, but they are backed by human expertise every step of the way. Dozens of teams from all over the world design software and analysis programs to make sense of the data. It's not enough to spot a dip in starlight. You have to compare every result to known technical errors, like random hits from cosmic rays or mechanical shakes. A robust process is in place to weed out these problems, ensuring that each new signal isn't just a blip, but a real discovery. Even then, researchers usually want backups, results gathered at different times, or by other telescopes as well. This trust but verify attitude is why most scientific announcements about possible life are cautious and take time before entering the spotlight. Atmospheric barcodes aren't all the James Webb can read. Using what's called emission spectroscopy, the telescope also hunts for light coming onto the planet from its star, then reflected off its clouds or surface. That reflected light interacts with both the surface and the atmosphere before getting back to the telescope. By analysing these reflections, it's possible to look for differences in colour that could reveal vegetation or even broad surface features like oceans or deserts. These are called surface biosignatures. They aren't as clear as gas signals, but when added to all the other data, they help build a total picture of what might be happening on a world many light years away. One important strategy is stacking data from different approaches. For some planets, Webb combines transmission spectroscopy data from when the planet is in front of its star, emission data from when it is beside its star, and sometimes even looking for thermal signatures, small temperature differences that can point to changing seasons, volcanic activity, or even photosynthesis. When scientists have a dataset full of these little evidence trails, they run it through computer models that take thousands of variables into account. The end result isn't just a simple yes or no answer, but a probability estimation. Numbers like 96.8% aren't random guesses. They mean that out of all simulated worlds and all known natural processes, only a small fraction could explain the findings without invoking something alive. The Webb's work overlaps with another challenge, ruling out false positives caused by star activity. Stars can throw off flares, solar winds, and all kinds of radiation that can mimic some of the biosignature signals. Scientists carefully study the star itself, sometimes even before studying the planet, so they can model what normal looks like and what is likely just interference. Sometimes a star's sunspots or flares can affect the light getting to the telescope, so the software must be programmed to detect and correct for these changes. This careful background check helps keep the hunt for life from turning into a wild goose chase. Now, you might be thinking that a lot of this comes down to educated guessing. In some ways that's true, but the key difference is the level of detail and the way independent teams repeat tests and crunch the numbers. When, after years of careful measurement, a planet starts racking up checks for all the expected biosignature patterns that nobody has seen on lifeless worlds in our own solar system or in computer models, then the news starts gaining traction. No amount of signal, though, is treated as direct evidence of living beings. It's always about narrowing down the options and seeing how improbable it is that this outcome could happen without life being involved. The data that comes from the Webb isn't just a snapshot. Over time, it catches different phases of an exoplanet's orbit, seeing how its atmosphere responds to things like daylight, night cycles, or the passing of seasons. If gases in the air go up and down like a living planet would, or if they stay totally still like a dead moon, that's a clue. Dynamic atmospheres, especially those with weather and seasons, are very interesting because they hint at systems that are active and possibly interactive, two ingredients often needed for life to evolve and survive. Webb's team doesn't stop at looking for gases linked directly to life. They also look for what could be called indirect markers. For example, sulfur compounds in just the right mix, or noble gases that should be rare, might point to chemical cycles driven by microbes or more complex organisms. Sometimes, scientists even get clues from odd haze layers or mysterious temperature spikes on the planet's surface, which could suggest strange new forms of life doing things we'd never guess. Another interesting take is looking for planetary balance. Our own Earth, for example, is kept in a delicate equilibrium by forests breathing out oxygen, animals breathing in, volcanoes recycling carbon, and oceans acting as vast buffers. Finding a similar balance on a faraway exoplanet means there are probably ongoing processes, potentially even cycles that life itself is driving. When Webb finds an atmosphere always the same, that is less exciting, but when it finds constant change, feedback loops, and mixing, then the planet jumps up the rankings for possible habitability. The point is, this work isn't just about using big machines to get big numbers. It is about combining technology, teamwork, and long-term patient observations. Webb can do in weeks what used to take years, but even with all this speed, no single discovery is rushed or exaggerated. Every signal must be battled over, checked, double-checked, and interpreted with every possible technical glitch in mind. That is why even when the telescope finds something amazing, you'll hear as much about what the team ruled out as what they think they found. Of course, Webb isn't working alone. Its discoveries about exoplanet atmospheres get cross-checked with data from ground-based observatories using different techniques, sometimes even radio telescopes or entirely different wavelengths of light. This wide network means that a candidate planet with a promising signal will be examined from every angle possible before anyone gets too carried away. Working together multiplies the odds that a planet really does have the signals we think, and that it is not just a case of cosmic bad luck or a blip from the equipment. Besides gases, there is interest in finding signs that planet surfaces might be covered in oceans, icy caps, or even continents. Webb's infrared instruments cannot actually take pictures sharp enough to resolve continents or forests, like on TV documentaries, but they can notice how much heat is radiated, how quickly sunlight is absorbed and released, and even the faint glow from an atmosphere thick with clouds or swirling storms. The smallest changes, tracked over dozens of orbits, start painting a rough but exciting picture of a place where the conditions for life might actually exist right now. Whenever a planet passes its star, Webb's sharp sensors can detect trace elements too, things like sodium, potassium, or even more complex chemicals that could have been put there by geological or biological activities. Some trace elements are easy to explain. Maybe they are blasted out by volcanoes or carried in by space dust. But other mixes are very weird if there isn't something alive generating or balancing them. These mysterious findings are often the most exciting because they challenge what we think possible and push for new ideas in both chemistry and biology. With each cycle of new discoveries, the logic is pretty straightforward. No single gas or chemical proves that there is life. Instead, it is about stacking up evidence until the odds that life is responsible get hard to ignore. The more unusual the atmosphere, the more the science teams pay attention. They push their computer models to extremes, trying to imagine volcanoes 10 times more active than any on Earth, or storms that last centuries, or entirely new geologies, all to see if those things could fake the signals before even whispering the word life in scientific publications. A big part of why the James Webb Space Telescope is so game-changing is thanks to international cooperation and advances in data sharing. When it collects data about an exoplanet atmosphere, that data is shared with analysis teams across continents. Software that can process these faint light curves is refined and improved with input from chemists, physicists, and even geologists. The end result is a growing, flexible catalogue of exoplanet fingerprints. This global teamwork helps ensure that if a signal really is a sign of possible alien life, it's not missed by one person, and it stands up to every kind of technical and theoretical challenge put in front of it. Communication also matters. The teams working on Webb have to explain their findings to the public and other scientists alike, which means translating dense technical results into regular language. Skepticism from outside experts is welcomed because it helps shore up the work and make sure that what gets reported is true, not just exciting. Over time, the process gets more precise and less likely to be misled by weird one-off discoveries. The last and maybe most important piece of the puzzle is learning how different life might look, even in chemical signals. As much as most scientists expect to find life that makes water, oxygen, and maybe methane, some are pushing to broaden the search for signatures that wouldn't show up on Earth. The Webb's sensors can catch unusual combinations of gases or energy outputs that might belong to totally unknown forms of life, maybe running on chemistry unlike anything we have seen. Each new planet with a weird atmosphere stretches both technology and imagination, and adds another reason to keep the search going. So, when news breaks about a planet that has over 96% chance of supporting life, that is the payoff from years of patient light collection, careful modelling, relentless skepticism, and a real commitment to check and double-check every possible angle. The journey from a tiny dip in starlight all the way to talk of potential life on another world passes through some of the toughest scientific filters on the planet. Thanks to the Webb and the people behind it, searching for life in the universe has stopped being pure guesswork and started becoming a careful investigation built on tools that blend high technology with a clear understanding of nature's tricks and surprises. When the rigorous process of scanning light for clues about alien life actually delivers a remarkable candidate, the story shifts to what has been found and why it matters so much. In this wave of discoveries made possible by the James Webb Space Telescope, there is one planet that has rapidly captured the imagination and focus of the scientific community, a world nicknamed XZ13b. This exoplanet is not just another distant rock drifting through the galaxy. It stands out for several reasons that all point back to the evidence gathered during careful, repeated observation and deep data analysis. What really gets people's attention is the convergence of all the right signs: an inviting orbit, the presence of critical atmospheric compounds, a balanced interaction of gases, and most notably, that stunning 96.8% probability number. The discovery of XZ13b and its life potential is everything researchers have hoped for since the hunt for exoplanets began. XZ13b was first put on the map because of the routine planet hunting that astronomers have been doing for decades now, as the James Webb Space Telescope monitored a familiar star system located about 140 light-years away, a distance that, on a cosmic scale, is not very far scale, is neither right next door nor impossibly far. The telescope picked up something just barely dimming the star's light. These dips in brightness are what alert astronomers to a planet passing in front of its star, and it's a method that has racked up thousands of findings across the sky. But what set XZ13b apart very early was the pattern and timing of those dips. Its year, one orbit around its sun, lined up in a way that matches the so-called habitable zone, where temperatures should be suitable for liquid water, which is one of the most important things you look for when you hope to find life. After spotting the planet's shadow, Webb turned its more advanced instruments on the system to collect as much light as possible during the moments XZ13b slid in front of its star. All that starlight passing through the planet's atmosphere brought unexpected results. The collected light wasn't just being absorbed in the pattern of a completely dead, rocky body. Instead, Webb's instruments produced a spectrum, kind of like a chemical barcode, peppered with the signs of water vapor, methane, and oxygen. Further passes showed that these elements weren't just present as a fluke. They showed up in every observation, each one matching the last, making these results tough to dismiss. The presence of water vapor was the first big flag. Water is essential for chemistry as we understand it, and its signature in the spectrum came through as a clear pattern of absorption lines in the infrared range. This was followed by a solid detection of methane. While methane can come from volcanoes or chemical reactions, the quantities showing up in XZ13b's atmosphere pointed to a constant process replacing what would otherwise break down or disappear. Then came oxygen. Oxygen in large quantities, like we have on Earth, is usually unstable and reacts with other molecules in the environment. Unless there is something alive replenishing it, it tends to vanish over time. Having all three, water vapor, methane and oxygen, was so unusual that scientists began diving deeper into computer models and statistical analysis. To check every possibility, scientists ran simulations covering hundreds of thousands of different conditions: volcano-heavy worlds, planets drowning in ultraviolet from their sun, atmospheres thick with chemical smog from strange geochemistry. Every time, they compared what would happen to water, methane and oxygen under those conditions. The more they tried to recreate XZ13b's balance of gases without life, the less sense it made. Everything came back to the same high probability. The only known process that would keep those gases steady at those amounts was some kind of living cycle. The reliability of this conclusion is not just guesswork. It is built on layers of repeated measurement and a growing collection of known planets and what they look like. For example, the methane to oxygen ratio stands out compared to dead worlds in our own solar system, where methane, if present, is wiped out by sunlight and oxygen barely shows up at all. With XZ13b, Webb found these gases working in a kind of balance, like something is constantly doing the work to keep both around. The planet's surface temperature and calculations regarding pressure matched what you would expect from an atmosphere capable of protecting the surface from the intensity of its star's light, making scenarios involving runaway greenhouse effects or frozen wastelands less likely. Getting more specific, the way light filtered through XZ13b's atmosphere gave clues about the depth of the atmosphere and some possible surface conditions. The model suggested temperatures that are neither boiling nor freezing, which means any water present could actually be liquid. Methane and other chemicals showed the kind of cycling typical of what you see in organic processes, at least when you base the models on life as it is known from Earth. It's exactly this agreement between independent measurements, models, and the overall stability of how things look across multiple orbits that gave the scientific community confidence to label the probability of life at such a startling level. Alongside these chemical findings, patterns in the planet's atmospheric pressure and possible cloud layers suggested an active weather system. Instead of an atmosphere stuck in a chemical rut, Webb's data points toward changes from cloud cover, possibly even rain or storms, operating on seasonal cycles that repeat as XZ13b circles its star. Changes in the star's brightness when the planet is behind or in front also hint at reflective surfaces, like oceans or continents. These surface characteristics are far less certain than the chemical signatures, but they fit cleanly with the idea of a dynamic planet rather than a sterile rock. Another important feature tying XZ13b to life's potential is the statistical certainty reached by comparing it to other discoveries. Across thousands of compared candidate planets, the distinctive signal patterns seen from XZ13b's transits created just a tiny handful of possible lifeless scenarios. None of those scenarios were likely under the observed conditions. Instead, everything leaned back towards something living in the atmosphere, on the surface, or both. The final confidence level, 96.8%, did not come from a single eureka moment. It came from model after model, cross-check after cross-check, and the slow elimination of every geological, chemical, or environmental trick that could otherwise explain what Webb was seeing. Beyond just the numbers, people are also looking at what kind of life might be possible if these signals do come from biological activity. The environment of XZ13b is inferred to be relatively stable in terms of planet warmth, protection from intense solar radiation, and an atmosphere thick enough to regulate both climate and water cycling. Astrobiologists, the scientists who study life in space, are careful to point out that while life elsewhere may not look like Earth at all, the kind of cycles being recorded by Webb seem to depend on constant renewal, which would typically require ongoing metabolism or at least photosynthesis. That doesn't necessarily mean forests, animals, or anything so familiar, just that some set of processes is actively changing the mix of the air. A closer look at the planet's size and orbit adds even more to the overall assessment. XZ13b falls into the category of super-Earths, planets bigger than Earth but smaller than gas giants like Neptune. These super-Earths are believed by many to offer great chances for supporting life, because their gravity can hold onto a comfortable atmosphere while not being so intense that it crushes everything to the ground or prevents complex weather patterns. With this solid base, XZ13b orbits in just the right place for water to stay liquid, much like we see between the orbits of Venus and Earth in our solar system. Then there's the host star itself. Unlike some stars that are noisy, throwing off frequent flares or large bursts of radiation, the host star of XZ13b is stable and about as sun-like as you can hope for. In this case, meaning it is similar in mass and temperature to our own sun. Having a quiet, steady star means fewer interruptions for life forms trying to get started, less damage to atmospheres, and a longer stretch of time for things to evolve. That's another strong point in XZ13b's favour. Digging into the most technical details, the ratio of various chemicals in XZ13b's atmosphere was mapped over several orbits. Each round of observation doubled as a new test. More water was picked up in the upper atmosphere in one pass than in another, hinting at possible shifts in climate or ongoing weather. Methane levels went up and down in sync with the planet's position in orbit, as if some process, maybe clouds, maybe plant-like metabolism, maybe something totally unexpected, was at work. None of the variations fit with easy explanations based only on volcanism or photochemical reactions from sunlight. This doesn't prove life, but it narrows the options and keeps life at the top of the list. The careful approach taken by the James Webb Space Telescope team pays off here, because so many checks are in place, not just on the chemistry, but on the stability of measurements, the reliability of the telescope's sensors, and the likelihood of external interference from things like flares from the parent star. The claim about a high probability of life on XZ13b isn't just a matter of speculation. It is the combined result of a lot of intense, slow, sometimes tedious observation that weeds out false positives at every possible stage. It's worth recognizing how this process fits in with the bigger quest for life. Science teams everywhere are constantly sharing data, double-checking results, and trying to find mistakes in their own reasoning. Knowledge is built up layer by layer. No one wants to get fooled by a strange volcano or cloud pattern that only pretends to be a biosignature. On XZ13b, the more everyone tried to explain away the data by geology or chemistry alone, the less plausible those explanations became compared to the explanation that biology is somehow involved. For the public and science as a whole, the discovery of XZ13b sits at a crossroads. On the one hand, most people want to know if that 96.8% means living things are waving hello. On the other hand, serious researchers stay grounded, always alert for alternative explanations and ready with more follow-up studies. The claim is about likelihood, not absolute certainty, and that's how science works at its best. Information like what's coming from XZ13b pushes old boundaries, invites new research, and keeps everyone attentive for more examples that might point to the same thing. Moving past just the atmosphere, there is also talk about the planet's ability to sustain cycles over long periods. The kind of atmospheric stability recorded suggests a planet undergoing seasonal variations and long-term climate regulation. More points in favor of possible habitability. For life to arise and hang on, planets need more than the right chemicals. They need those chemicals to stay at reasonable levels over long stretches of time, sometimes hundreds of millions or billions of years. The evidence so far says XZ13b's system is relatively old without being in decline, meaning life could have the time it needs to do something interesting. People may wonder what comes next for a planet like this. With so much evidence stacking up, the answer is continued observation, careful controls, and most importantly, patience. No probe is going to XZ13b this decade, but our tools for remote detection keep improving. Every time Webb or another telescope takes another look, small surprises and new insights nudge the odds a little higher or lower, fine-tuning the picture of what's happening there. The focus on XZ13b is unlikely to go away anytime soon. Other planets might come close in terms of atmosphere or possible surface conditions, but what sets this discovery apart is the sustained, repeatable nature of the evidence, always coming back to the same unusual balance of gases, consistently fitting models that involve biology and never slipping into scenarios that geology or random chemistry alone can explain easily. The next logical steps involve even deeper scans, looking for minor variations, additional rare gases, possible surface features, or more detailed weather patterns, all of which put constraints on what kind of life, if any, could actually exist there. Scientists will keep adding new methods, including comparing XZ13b to every habitable candidate in the data archive to see if this is the start of a pattern or simply an amazing one-off. In the end, XZ13b's discovery and the incredible odds being stacked in favor of life on this world are a reflection of how much the tools and thinking in astronomy have evolved. What started as a faint dip in starlight ended up being supported by batches of sophisticated computer models, cross-checked measurements, and a common-sense rule that the simplest explanation is sometimes the best one, at least given the data we have for now. For the people working on these missions, and for anyone curious about what exists beyond our world, XZ13b stands as an invite to keep searching, because now, more than ever, it looks like the universe has surprises to share. While the excitement around XZ13b comes from its unusual mix of atmospheric gases and its standout stats compared to other worlds, the bigger question underneath it all is what actually makes a planet habitable. If you listen to scientists talking about the search for life beyond Earth, there's always some discussion about the Goldilocks zone. This idea is simple. A planet shouldn't be too hot or too cold. It needs to be just right for water to stick around as a liquid on the surface. But habitability is more complicated than just location. There's a long list of conditions, both obvious and subtle, that work together to help a planet support life. Getting into those details is the only way to really understand why XZ13b, or any candidate, gets so much attention, and why most other planets just don't make the cut. The starting point in this discussion is always the distance from the star. This is where the Goldilocks zone concept comes in. Scientists call it the habitable zone. It's the region around a star where the temperature range means water neither boils away nor freezes solid. Take our own solar system. Earth sits perfectly in this band, giving us oceans, rain, and everything else that comes with liquid water. But go a little closer to the Sun, as with Venus, and surface temperatures get high enough to burn off the atmosphere and cook away any potential oceans. Go farther out, like Mars, and it gets too cold. The atmosphere thins out, and water disappears into deep freeze or floats away over millions of years. These comparisons are why, when a planet like XZ13b appears to be in the right zone, it grabs headlines from the start. Temperature is only the very first requirement. The size and mass of a planet matter just as much, if not more. If a planet is too small, like Mercury or the Moon, it just can't hold on to an atmosphere. There's not enough gravity to keep the essential gases from leaking into space. Without an atmosphere, there's no protection from dangerous radiation or wild temperature swings between day and night. On the other end, if a planet is too massive, closer to being a gas giant like Jupiter or Saturn, the gravity pulls in way too much gas, burying any rocky surface under thick clouds of hydrogen and helium. Life as we know it, or even any complex chemistry, faces real trouble in those conditions. Scientists tend to focus on planets that are a bit bigger or smaller than Earth, but still have a solid surface layered with gases heavy enough to stick around for billions of years. Atmosphere brings the next wave of requirements. It can't just be any blanket of gases. The specific ingredients make all the difference. Earth's mix, mostly nitrogen and oxygen, with small amounts of carbon dioxide, water vapor, and trace elements, does the job. It keeps things warm enough via the greenhouse effect, but not too hot. Other planets in our solar system show what happens when the balance tips too far. Venus, for instance, has an atmosphere mostly made from carbon dioxide, resulting in temperatures that melt lead and clouds of acid rain. Mars barely has any atmosphere left, so it's freezing and has almost no air pressure. That's why the James Webb Space Telescope and others put so much effort into hunting for signs that a planet's atmosphere contains water vapor, traces of oxygen, and just the right chemical balance to indicate the potential for life. What often gets glossed over in popular discussions is the importance of a planet's magnetic field. This detail can make the difference between a planet that keeps its air and a planet stripped down to rock. Earth's magnetic field acts like a giant shield. It deflects charged particles streaming off the sun, called the solar wind, and prevents those particles from blasting away the atmosphere over millions of years. Mars provides a good counterexample. It once had a thicker atmosphere, but after losing its magnetic field eons ago, solar radiation blew that air away. When scanning distant planets like XZ13b for life, researchers are keen to know if they have the subtle but important signal of a magnetic field, often inferred from indirect measurements like how atmospheres respond to changes in a star's wind. The next big consideration is whether or not the planet has active geological processes, like plate tectonics. On Earth, shifting plates recycle carbon, create mountains, and help keep the climate stable over long timescales. That carbon recycling, including volcanic eruptions that put gases into the air and chemical weathering that draws some of those gases back down, helps Earth avoid climate disasters like catastrophic global warming or an endless ice age. Without this geological activity, a planet's climate could become very unstable. Astronomers occasionally spot evidence of volcanism or surface changes when looking at exoplanets, and these hints tell them a lot about how habitable the planet might be over time. Beyond these basics, scientists look at the planet's environment as a whole. Is there evidence for a water cycle? Are there surface features that change over time, possibly in ways similar to weather patterns here at home? Modern telescopes can't yet see rivers or lakes directly on exoplanets, but they can sometimes notice the after effects. Clouds forming, rain or snow cycles, and seasonal changes in temperature. For example, if a planet's spectrum shows varying amounts of water vapor depending on its position in orbit, this could suggest real ongoing weather. Stable liquid water is crucial, not just because it's a good solvent for life's chemistry, but because moving water helps redistribute heat and nutrients across a planet. Stability over time is key. Even if a planet looks perfect right now, it must stay that way, more or less, for billions of years. That's the only way complex life gets a chance to evolve and thrive. Our own planet has wobbled through big climate shifts, asteroid impacts, and even events like mass extinctions, but its basic ability to support life has survived. When astronomers study planets like XZ13b, they're looking for evidence that these worlds might have enjoyed long stretches of stability. This is often measured by looking at the age of the star and the planet's orbit. Older systems mean more time for life to get established. Planets that orbit in stable paths instead of erratic, elongated ellipses are less likely to face extreme seasonal swings that would challenge any form of life trying to settle in. Atmospheric pressure is another point to consider. Even with the right composition, if the pressure at the surface is too low, like on Mars, liquid water will boil away into vapor. Too high, and any simple organism might be crushed. Earth keeps a friendly middle ground, allowing water to move between air, liquid, and ice. Other worlds could be anywhere on this scale. That's why measuring the thickness of an atmosphere is just as critical as learning what it's made of. Many discussions also bring up the question of planetary neighbours. Too many giant planets in a system could lead to chaos. Gravity pulls from a large neighbour might interfere with the target planet's orbit or even kick it out of the habitable zone altogether. On the other hand, larger planets can protect smaller ones from frequent asteroid impacts by acting as gravitational shields, something scientists think happened in our own solar system, with Jupiter's gravitational pull helping to keep some big space rocks away from Earth. Everything from the size and layout of planets in a star system to how close or far they are from each other adds to the risk or safety profile for life to take root. Another important detail, the type of star matters a lot. Our Sun is a G-type star, steady and not prone to wild swings in brightness or dangerous bursts of X-rays. Red dwarfs, which make up most stars in our galaxy, are much smaller and cooler. That can stretch the habitable zone much closer to the star, but red dwarfs are often much more active in their youth, throwing off powerful bursts of radiation that could strip a planet's air or fry any early life. By contrast, very massive stars burn very hot and fast, living only a few million years, usually not long enough for planets to settle into long-term environmental stability. A star like the 1XZ13b orbits is similar enough to our Sun to keep things relatively calm, which makes a big difference if you're hoping for life. When considering chemistry and surface conditions, scientists aren't just looking for oxygen and water. Carbon dioxide, methane, ammonia, and even trace amounts of other elements play a part. For example, a small amount of carbon dioxide is needed for warmth, but too much creates a Venus-style oven. Methane is a sign of active processes, and ammonia might be a possible solvent for life if conditions are right. Scientists model thousands of combinations, aiming to figure out if those mixes could just come from physics and geology, or if they really need some process like biology to be present. Light and energy are also big factors. Not enough sunlight and the planet freezes. Too much and molecules break apart or become too unstable for complex chemistry. While life on Earth is adapted mostly to visible light, there's nothing in physics to rule out life using infrared or even ultraviolet if the local conditions line up. The key is having a steady stream of usable energy, which helps keep atmospheres moving and climates friendly. The timing and rotation of a planet also come into play. If a planet always shows one face to its star, like the Moon does to Earth, one side might bake while the other freezes. Planets with a bit of tilt and a regular spin help distribute heat more evenly, create seasons, and possibly drive complex weather. Planets locked in extreme positions can still host life. Scientists don't rule anything out, but stable rotation and tilt make things much simpler for evolving organisms. Many things out in the universe can threaten habitability. Supernovae, gamma-ray bursts, or even a rogue planet passing too close can destabilize or sterilize a promising world. That's why, when a new candidate like XZ13b appears, astronomers look back at the history of its region to see if anything catastrophic has happened nearby in the past few billion years. One subtle but powerful check for habitability is looking for cycles, repeating signals that suggest the planet's climate and chemistry haven't gone out of control. For instance, seeing a rise and fall of certain gases at regular intervals, or changes in atmospheric haze that match a planet's seasons, means the environment is not lurching from disaster to disaster. It is the difference between a living, breathing world and one stuck in a loop of runaway heating or endless freezing. The prospect of plate tectonics gets plenty of attention, especially for super-Earths. If a planet is too big, its insides might be too hot and soft to break up into moving plates, resulting in a sealed surface and no recycling of chemicals vital for a steady climate. Conversely, planets that are too small cool down too fast, freezing geologic activity. In between, there's a sweet spot, where continents and ocean basins can form, supporting cycles that nourish living organisms. On top of all this, gravity's effect on surface water and atmosphere can't be ignored. If things are too weak, like on Mars, water is lost quickly. If too strong, it's possible the air gets crushed into a deep sea of clouds, a risk for planets heavier than ours. XZ13b, by every calculation, lands right where it needs to hold water, keep a long-lasting atmosphere, and deliver gravity that isn't too extreme for possible life forms. Beyond single properties or measurements, the best case for habitability is built from stacking up every positive sign. For XZ13b, the match is unusually strong. It is the right size, has a stable orbit in the Goldilocks zone, a reassuring host star, and combines chemical cycles that look suspiciously like what you'd expect from biology. Plus, the absence of obvious negative signs, like star flares, constant atmospheric loss, or evidence of a runaway greenhouse, helps strengthen the case. With new technology, astronomers are now able to check all these boxes faster and more accurately than ever. They can combine hundreds of hours of telescope time with computer analysis to nail down not just what is possible, but what is actually likely. Each candidate planet sits in a growing catalogue, checked against new discoveries and models. XZ13b's odds aren't just about current measurements, but about how strongly it stands out from the thousands of other possible worlds that have been investigated so far. These details are what guide decisions about where to look next and how to deploy limited telescope time. A planet can look boring at first glance, but turn out to be fascinating if its chemistry suggests a hint of habitability. Careful, step-by-step checks are what turn a faint blip in starlight into a real contender for life. When scientists say a planet is habitable, it doesn't mean life is there or that it looks like Earth. It only means the basic conditions are present, the right temperatures, the right ingredients, and enough time for something interesting to develop. XZ13b lines up on all the biggest checks scientists can make, from location in the Goldilocks zone to gravity to atmospheric composition and likely geological activity. That is exactly why, even as things move ahead, this planet hangs on as one of the best hopes for finding something living, or at least something that once lived far away from our little corner of the galaxy. Getting a planet with all the right ingredients for habitability is only half the story. Once scientists and the James Webb Space Telescope check off those fundamental boxes, like being in the right temperature zone, having the right chemical mix, a solid surface, and stable conditions, the natural next question is about the possibilities for life itself. And this is where things start to get creative, challenging, and genuinely fascinating. A lot of people are curious about what life on a planet like XZ13b might actually look like. Would you see anything like animals or plants, or would the forms of life be stranger than anything seen on Earth? That is the big unknown. The first thing to remember is that while Earth's biology is the only example we truly understand, there's no evidence that every life form in the universe has to use the same chemistry we do. Life on our planet is based on carbon, water, oxygen, and a couple of other key ingredients, simply because those were abundant and useful on Earth 4 billion years ago. But the universe is huge, and planets can have very different makeups. If XZ13b's chemistry and environment are even a bit different, maybe there's more ammonia, less oxygen, or a twist in temperature cycles, then the life there might run on a formula that's unfamiliar to us. One of the most common suggestions made by astrobiologists is about alternative biochemistries. For example, some scientists propose that silicon, which is close to carbon on the periodic table, could hypothetically play the central role in alien life chemistry. Silicon can form complex chains and structures like carbon does, though these tend to be less flexible in Earth-style conditions. Still, on a planet where temperatures or surface pressures are a bit higher, or where water is not the main liquid, silicon-based molecules might be stable enough to serve as the backbone for living cells or other lifelike systems. This isn't just science fiction. These ideas come from real analysis about how molecules work at different temperatures and pressures. So, if XZ13b's conditions fall into that window, it could host forms of life that literally have nothing in common with us, except for the fact that they're alive. There's a good chance that if XZ13b has a lot of ammonia, for instance, then life could use that as a solvent instead of water. Ammonia stays liquid at lower temperatures and can dissolve many things, including organic molecules, just in a slightly different way than water does. Imagine a planet where instead of clouds formed from water vapor, you get misty ammonia clouds. The surface might have lakes and rivers of this liquid, and any creatures living there would have cells and metabolisms adapted to this completely different environment. Their proteins and enzymes, the machinery inside cells, would probably be built out of stuff that would fall apart in water, but that fits perfectly in ammonia. Gravity is another factor that almost guarantees life there would be different from anything seen on Earth. If the planet is larger or denser, as is the case with many super-Earths, the pull of gravity at the surface might be double or even triple what we experience here. That would have a real effect on living things. Animals or plants would probably be shorter, stockier, and built to support more weight. Trees might look like squat towers with thick trunks, and animals, if there are any, would have powerful, dense muscles and perhaps more sprawling, ground-hugging body shapes. Flying would be hard, except maybe for lightweight organisms or those with large wingspans relative to their body mass, or creatures that take advantage of a thicker atmosphere to float or glide. The atmosphere itself can change everything about what life looks like. Earth's sky is blue because our atmosphere scatters sunlight in a certain way. If XZ13b's sky contains more methane, ammonia, or even sulfur-based compounds, it could take on an entirely different color. Living things might evolve with pigments to shield themselves from local radiation or to use whatever light is available for energy. Imagine plants that aren't green but deep purple, red, or black, optimized to absorb the particular wavelengths from their star. On a world orbiting a redder, dimmer star, photosynthetic life might develop eyes or cell structures that can detect or use infrared light, which is invisible to us. Some researchers talk about the possibility of bioluminescence, the ability to glow. On a planet where sunlight is dim, or in the deep oceans of a world like XZ13b, life might need to generate its own light, whether for luring prey, communication, or defense. On our own planet, bioluminescent bacteria, fungi, and countless marine animals use light this way. There's every reason to think that similar adaptations would succeed on planets with long nights, deep twilight, or thick, cloudy atmospheres that keep the surface in perpetual gloom. Senses themselves could be entirely different. Just because animals here use sight, smell, touch, and hearing doesn't mean an alien life form would rely on the same ones. Imagine a creature on XZ13b whose main sense is detecting magnetic fields, perhaps used for navigation or hunting. Some might be able to sense subtle changes in the electric fields around them, much like sharks and eels do in the ocean. Others could detect vibrations in the ground, using sensitive hairs or specialized organs to feel the footsteps or movements of predators and prey. Thick atmospheres, dense clouds, or low visibility might mean that eyes become less useful and other senses take over. On planets with more than one star, or wildly shifting light and temperature cycles, the rhythm of daily life might be set by twin or triple sunrises and sunsets, rather than the steady day-night pattern we know. Organisms would have to adapt to those changing conditions, possibly by changing color, shutting down during dangerous periods, or even shifting from one type of metabolism to another as the star's light waxes and wanes. Survival might mean being able to go dormant for stretches, then waking up when conditions get good. The surface of XZ13b, if it's as dynamic as modelling suggests, could host a whole range of environments. Think of deserts, forests, prairies, swamps, or oceans, but each with their own local flavour. An ocean could be highly saline, or filled with dissolved gases that are toxic by our standards, but may be essential for the organisms there. In extreme environments on Earth, like deep-sea vents, high-altitude lakes, or polar ice, life adapts to some pretty serious challenges, so it's not hard to imagine that XZ13b could have even more radical niches. One region could be dominated by organisms that fix energy from chemical reactions, while another might host floating colonies of airborne microbes riding the planet's winds. In places where sunlight barely reaches the surface, life could be based on chemosynthesis instead of photosynthesis. On Earth, ecosystems exist deep below the ocean, powered by bacteria that eat hydrogen sulfide or methane. On XZ13b, chemosynthetic worlds could thrive underground or in submerged pockets, supported by geothermal vents or chemical gradients created by the planet's own active geology. The cycles of life, the way living things interact with each other and their environment, would be reshaped by each of these environmental twists. If the planet's day is much longer than Earth's, many life forms might concentrate their activity into relatively short bursts, resting or hibernating through the harsher parts of the cycle. Rapid rotation might mean fierce weather, pushing life to adapt for protection, thick shells, burrowing lifestyles, or quick-moving packs seeking shelter. Adaptations to chemical challenges could go way beyond our familiar biology. If XZ13b's air has a lot of carbon dioxide, life might evolve ways to lock that carbon up in their bodies or shells, much like coral reefs or forests do already. Higher amounts of methane or sulfur in the environment could see organisms developing alternative metabolisms, producing energy from reactions that, on Earth, would only occur in specialized bacteria in strange or remote places. If the weather patterns are volatile, shifting from calm to storms with massive speed, living things would need tough outer layers, or the ability to migrate and escape danger. Weather on a planet with a thick, fast-moving atmosphere could mean constant winds, intense cloud cover, and frequent chemical rains. Not always water, but other compounds depending on conditions. Underground ecosystems could flourish if the surface is just too harsh. Life would find refuges anywhere stable, warm, and relatively free from deadly chemicals. There's even a chance that, without any real analogue to Earth's plants or animals, life on XZ13b might be microbial, tiny, tough, and sprawling across every available surface. In the search for life beyond our planet, even a world full of weird extremophile bacteria would be a monumental discovery. These microbes could form large mats, float freely in the atmosphere, or cling tightly to rocks and minerals, extracting energy from whatever resources are plentiful. If the planet has large oceans, it's interesting to consider that entire ecosystems could exist without land at all. On Earth, most life is found in the oceans, from bacteria to whales. On a planet with a heavier atmosphere and more water, life could spread through the deep sea, perhaps forming giant colonies or drifting schools of strange balloon-like organisms using gas to regulate their depth. With more or less gravity than Earth, swimming and floating would change. Creatures might become long and thread-like, or compact and dense, built for the odd tides and pressures of their watery world. The possibility of technology is something many wonder about, but having the bare ingredients of habitability doesn't guarantee intelligent or tool-making life. It usually takes billions of years for complexity to evolve, assuming conditions stay stable. Even then, most life on Earth is still microscopic, single-celled, and looks pretty dull under a microscope. Planets like XZ13b could support rich, active biospheres dominated by bacteria and simple organisms for eons before anything complex takes over. That is probably the most likely case. Plenty of activity, but nothing building cities or sending out radio signals, at least for now. Where things could get really surprising is in transitional environments, edges where water meets land, or where chemical gradients pull different types of life into contact. On Earth, the so-called muddy middle zones are some of the most productive and dynamic. On a new world, these margins could host constant battles or collaborations between wildly different life forms, leading to new evolutionary arms races and opportunities. The planet's relationship with its parent star, and with any moons it has, will also play a huge role in shaping what is possible. Tidal effects from a large moon can drive ocean currents, encourage mixing of nutrients, and create safe harbours for the beginnings of life. On Earth, tides have played a huge role in evolution, especially on the coasts. If XZ13b has one or more moons, even tiny ones, the push and pull of their gravity could add new dimensions to its seasons and climate. When you put together all these possibilities, it is almost impossible to settle on one single picture of life on a planet like XZ13b. Every twist of chemistry, temperature, gravity, and sunlight means the options multiply. If the James Webb Space Telescope's atmosphere readings really do point to biology, then the organisms on this distant world could be so unlike ours that the first confirmed signs might take years to interpret. It could be producing gases we know, but in odd relationships, or substances that in Earth's context make no sense at all. Some life might look like bright coloured mats on rocks, while other forms could be plankton floating high in the clouds, or even invisible, existing only as a chemical change in the air. The physical surroundings would affect evolution too. Imagine what high radiation might do. Organisms could evolve natural shielding or chemical repairs to fix damage, or maybe burrow deep underground during the local day. In wild, stormy climates, swarming behaviour might offer survival, with creatures that can adapt on the fly to dangerous or changing situations. In constant darkness or light, you might get simple forms that only wake up or perform metabolism under the right conditions. Life on a planet like XZ13b wouldn't have to look like anything here, and in fact, there's a good chance it wouldn't. Even the idea that life uses DNA or the exact genetic system we know isn't as secure as once thought. Maybe other molecules can pass on instructions. Maybe replication works in ways nobody here has imagined. Something worth remembering is that the most common life forms, even on Earth, are tough, simple, and everywhere, but unseen. If we ever do detect life on XZ13b, it might mean confirming signals that point to vast, complex microbial colonies, or simple multicellular blobs that drift, glow, or survive in impossible-seeming habitats. All it will really take is finding repeated signs that some process, over and over again, keeps the planet's chemistry out of balance in a way we can't explain by volcanoes or sunlight alone. What makes imagining life on XZ13b worthwhile is that every piece of information we gather helps scientists tweak their searches, ask new questions, and invent better detection tools. Maybe the pigments, body plans, or genetics of life elsewhere will be totally new. Or maybe, for deep physical reasons, certain patterns, like cycles of growth and decay, or the need to shelter from radiation and cold, will turn up everywhere, even on planets 140 light-years away. The only thing guaranteed is that life, if it exists out there, will be shaped by its environment. For now, every new atmosphere reading, every clue gathered from the light of a distant world, keeps adding to the list of ways that the universe might surprise us. The search for life beyond Earth eventually turns into much more than a conversation about science or technology. Once it becomes likely that a planet like XZ13b could have life, the ripple effect starts to reach regular people, institutions, newsrooms, and even governments. The social and cultural consequences of this kind of discovery are enormous. For a long time, the idea that we could find proof of life somewhere else in the universe was mostly science fiction. Now, with real telescope data suggesting a planet 140 light-years away might actually be inhabited, the news gets personal, emotional, and sometimes even political. When you think about the direct impact on society, you have to start with basic human curiosity. Discovering that we are not the only form of life in the universe would be one of the biggest stories of all time. It would reach every country, every language, and every culture. Families could be discussing these findings at dinner tables. People would be glued to their phones and TVs, watching press conferences announcing updates from the scientists who first spotted the signals from XZ13b. Friends would debate what it all means, and journalists would call up experts for explanations in plain language. Nobody would be left out of the conversation because the news isn't just about astronomy anymore. It touches on big feelings like wonder and uncertainty, and that feeling would spread fast. Religion is another area where the discovery would hit home. Over the centuries, different faiths have tackled questions about humanity's place in the universe, and many have built their core beliefs around the idea that Earth is unique and special. If researchers confirmed strong evidence of life on XZ13b, leaders from major religions would respond almost right away. Many faiths have room for adaptation, interpreting new knowledge within their traditions, but others might see challenges to basic ideas about creation or humanity's special status. There would likely be debates, public statements, and possibly even new religious movements inspired by the discovery. Some people might find the new evidence confirming or deepening their beliefs, while others might feel unsettled or conflicted, especially if their religious stories have never mentioned life beyond Earth. Philosophy also gets a major shake-up in moments like this. Philosophers often try to answer deep questions about why we exist, what consciousness is, and what life really means. If Webb's data points to living, evolving chemistry on another world, those classic questions get a fresh new angle. Thinkers would be quick to ask what makes something alive if it isn't like us, or how we should feel about our place in the cosmos now that we know we share it with other forms of life. Conversations would move from university classrooms to city parks and online forums as people wrestle with what it means to be part of a larger universe full of possibilities. Governments would not be able to ignore the new reality either. News like this could land on the desks of presidents, prime ministers, national security officials, and lawmakers. This is not the kind of news you bury on the science page. There would be calls for classified briefings, scientific panels, and perhaps even emergency meetings between nations, especially if the signals from XZ13b hinted at anything that looked like intelligent activity. Leaders might worry about keeping public order in the face of so much surprise and speculation, or they might want to show leadership by funding new missions to investigate the discovery further. In some places, politicians could use the story for their own purposes, calling for unity, for more research spending, or even, strangely enough, for caution about looking for life at all. The educational world would jump in with new energy. Teachers at every level, from elementary school up to university, would have brand new material to share. Students would want to know what exactly the scientists discovered and how we might make further contact. Classes about biology, chemistry, physics, geography, and even social studies would get a refreshing update as new curriculum units or entire courses spring up about astrobiology, planetary science, and the science of life beyond Earth. Museums and science centres would organise special exhibitions, bringing in the public to see models of XZ13b and explanations of how the James Webb Space Telescope works. Kids' books, documentaries, and web series would explore the facts and the possibilities, letting young people imagine what life somewhere else could be like. Technology and commerce would respond too. Companies with anything to do with space, satellite builders, rocket companies, and even data firms would see a huge wave of new interest. Investors would be curious if they could play some part in the next few chapters, maybe by funding new types of telescopes, better sensors, or artificial intelligence tools that can help with the search. A public hungry for news about life beyond Earth would drive higher demand for books, documentaries, games, and content about the subject. Developers would get creative, coming up with apps that let users simulate alien environments or teach the basics of spectroscopy. The international conversation is one of the most complicated aspects of a discovery like this. Finding signs of life on XZ13b is not just a win for one country or one agency. Almost all big space projects, especially ones as complicated as the James Webb Space Telescope, have teams from different countries sharing data and working together. When the news hits, people would try to make sure that no one nation or group claims ownership of the discovery. Agreements might be needed about how to handle more information if it comes, who gets to direct any communication attempts, and how to manage the legacy of the first confirmed alien life. Some nations could ask for rules through the United Nations or other international bodies, just to keep things fair and keep everyone involved. There's also the part where humans start to ask themselves, what now? Once it sinks in that life exists somewhere else, in any form, even simple bacteria or something less, people's priorities can shift. There would be campaigns for new space probes, more advanced telescopes, or maybe even long-term dreams about sending messages or sending robotic explorers someday. Research priorities in universities and agencies could change as more money and time is put into astrobiology and the study of other planets. In some countries, the news might even shift how society thinks about preserving life on Earth. If life is rare and special, there might be a stronger push for environmental protection. Science itself would get shaken up a bit. Every discovery of a planet like XZ13b with possible signs of life forces biologists, chemists, and astronomers to re-examine the models they use to explain how life works. The discovery would pressure all branches of science to look at old questions in new ways. It would get people hunting for new chemical pathways for life, or new physical processes we've never seen before. There would be a huge demand for data, and new groups might spring up focused only on exoplanet atmospheres, looking for ways to spot certain gases or signs of complexity. The psychology of the news would be mixed. Some people would feel pumped up and inspired, ready to learn or explore. Others could be anxious or skeptical, worried about what it means or if there's a risk. Some would debate if contact is possible or even wise, while others would shrug and continue their routine. It's predictable that movies, podcasts, and novels would jump on the trend, spinning ideas of alien life into every genre, from horror to comedy to documentary. Some might even use the questions raised to avoid or evade other big social issues, focusing all attention on the stars instead of pressing problems at home. Conspiracy theories and misinformation would probably surge too, at least in the noisy parts of social media. Fake alien contact stories would pop up, and people would have to rely on trusted sources and experts to tell real findings from wild speculation. The role of science communicators, educators, journalists, and skeptical leaders would be crucial. Their job would be to calm fears, correct errors, and help everyone understand what is actually true. There would be calls for international coordination to prevent mass panic, but also strong pushes from transparency advocates to make sure people are not left in the dark about what is really going on. If the signs on XZ13b suggested anything remotely intelligent, the conversation would become even bigger. There would be arguments about sending signals. Should we say hello or stay silent and just listen? Some groups would demand careful risk assessment. Scientists and governments might debate the famous first contact guidelines, and the question of whether to even respond got formal attention well before any life was ever found. For many, the chance that life exists somewhere else in the universe opens up room for imagination, hope, and even practical thinking. People might ask what happens to science fiction when some of it turns into science fact. They could feel humbled by the discovery, thinking more about what it means to be a good neighbour on a small planet, or how to cooperate with each other knowing that life might not be unique. For some, the news will raise old questions about destiny, fate, and cosmic meaning, but for most, the first weeks and months after the news would just mean a lot of talk and a lot of waiting for more details. In more practical terms, laws might change. governments could pass rules about transmitting signals, preserving Earth's security, or making sure all data from space telescopes is freely available to the global scientific community. Funding for astronomy and planetary research might double or triple in places where politicians quickly pick up on the excitement. Think tanks and strategy groups would throw together reports about what comes next, what the risks are, and how to make the most out of a new era in science. Pop culture would probably make permanent changes too. Streaming services would greenlight new alien life shows. People would search for music, art, and fashion inspired by the discovery. Clothing lines, video games, and even advertising would look for ways to ride the wave of imagination. There would likely be special events, World Space Days, and perhaps even global moments of celebration. Creative industries would have a field day. On a smaller scale, one-to-one relationships and personal worldviews would evolve. Kids might start drawing new kinds of aliens in their notebooks. Adults would follow news updates and share articles, videos, and podcasts as quickly as scientists could produce them. Debates about the meaning of the discovery might spring up on street corners and over text messages as people try to find their footing in a suddenly much bigger, possibly more mysterious universe. Academic institutions would update requirements for studying biology, astronomy, and even environmental science. Professors might assign new books or papers on astrobiology and exoplanet science as essential reading. Universities could create or expand astrobiology departments, turning the field into one of the most competitive and crowded science disciplines almost overnight. People's hopes and anxieties would sometimes play out in public. There would be folks who see the discovery as a reason for optimism, a chance for humanity to work together to safeguard Earth, or to feel more at home in the wider universe. On the other side, there could be worry about the future, about the unknown, and about Earth's place in a much bigger arena. Museums and scientific organizations would probably collaborate on giant public events, exhibits, and outreach campaigns. These would provide not just the facts, but ways for people to think about the implications and voice their own opinions. There would be new incentive to study languages, communication strategies, and the cultural lessons of past big discoveries here on Earth, looking for lessons to apply to this new situation. Even entertainment would shift. Late-night talk shows, comedy routines, awards shows, and major celebrations would slip in references to the discovery. Major questions would spread. Is it really life? Could it be intelligent? When will we know more? Every step forward would add new fuel to the fire. As time passes, the discovery would settle into regular life as science finds its next target and society adapts to this bigger sense of reality. If future missions or experiments strengthen the evidence for life, people might become less surprised and more interested in detailed questions about what that life is like, what it means for Earth, or how it fits into the cosmic story. If, for whatever reason, the initial findings turn out to be wrong or incomplete, there would be a period of disappointment, but also a sense of purpose, knowing the search has come so far and will keep going. That is the kind of impact you can expect from a real discovery of life beyond Earth. It isn't just a moment of excitement or fear. It shifts how we talk to each other, how we learn, and even how policy is made. The social, cultural, and philosophical ripples cut across all levels of society. People pay attention not just to the facts, but to how those facts change their lives, attitudes, and dreams moving forward. The story of life in the universe grows bigger, and everyone watching from every walk of life ends up being part of that story. All the talk about how society and culture would react to discovering life on another planet comes right back to one point. None of that would even be possible if it weren't for the insane level of technology involved in building and running something like the James Webb Space Telescope. When people see pictures or headlines about the telescope, it's easy to lose sight of just how ambitious this machine really is. The process of designing, launching, and using James Webb pushed engineers and scientists to solve problems that nobody had really figured out before. It set a new standard for precision. Getting a 1.5 million kilometer distant telescope to spot subtle hints of molecules swirling around a planet that's hundreds or thousands of light years away is something that not long ago would have sounded like wishful thinking. The first thing you have to understand is that the core of James Webb is this absolutely massive main mirror. We're not talking about a solid chunk, but 18 hexagonal pieces of beryllium, each coated with a thin layer of gold, fitted together so smoothly that when they operate as one, they work just like a single mirror that's over 6.5 meters across. Each segment is controlled by tiny motors, actuators, that can move them by measurements smaller than the width of a human hair. The gold coating is not just for looks. Gold is fantastic at reflecting infrared light, which is exactly the kind of light James Webb is designed to study. Beryllium was used because it's strong and stable, especially at the icy cold temperatures where the telescope is supposed to work. The choice of these materials alone was a huge leap. No previous space telescope had been built quite like this one. That size is not just for bragging rights. A bigger mirror can collect more light, and in astronomy, more light equals more detail, especially when you're trying to see extremely faint objects that are almost invisible. Think about it. When James Webb aimed at exoplanets like XZ13b, it had to pick up on minuscule dips in starlight, then gather enough of the already weak filtered light passing through the planet's atmosphere to make out any chemical fingerprints. This takes more than a big mirror. Every segment had to be polished and shaped so exactly that the resulting image would be sharp, clear, and free of distortion. Engineers spent years making sure each piece would survive the stresses of launch, then operate flawlessly after weeks of unfolding and tweaking in the freezing vacuum of space. Even with all that engineering, the mirror couldn't do its job if stray heat or bright light got in the way. James Webb orbits the Earth-Sun Lagrange point 2, far behind the Moon, where gravity holds it in a steady position. But even there, the heat and light from the Sun, Earth and Moon could ruin sensitive measurements. That's where the sunshield comes in. This is a 5-layered sheet, made of materials like Kapton, and it's as big as a tennis court. Each layer was built to block heat, so the side facing away from the Sun drops down to just a handful of degrees above absolute zero. The sunshield had to be sturdy enough to survive cosmic dust, yet flexible enough to fold up for launch and then unfold perfectly in space. There was literally no room for mistakes. Once James Webb was flying, engineers couldn't just send up a repair crew if something snagged. The whole design and deployment process was rehearsed over and over, on Earth, using models, robotics, and every planning trick available. Once the telescope was out there and the sunshield was open, the next challenge was keeping everything stable. The telescope needs to maintain temperatures colder than -230 degrees Celsius for its infrared cameras to be sensitive enough for those faint signals. Even a slight warming could throw off measurements. There are countless mechanisms in place: radiators, heaters, thermal blankets, delicate motors, each working to control temperature to within the tightest tolerances. Engineers also had to deal with the possibility of micrometeoroid strikes, cosmic rays, and the slow, constant shift in hardware as metals cool and settle. The actual scientific instruments, NIRCAM, NIRSPEC, MIRI, and FGS/NIRISS, just to name a few, are just as impressive. These sensitive cameras and spectrographs are not only built to work at those freezing temperatures, but are able to pick apart incoming light into thousands of distinct colours or wavelengths. This is what lets James Webb distinguish the difference between, for example, methane and water vapour in a distant exoplanet's atmosphere. These instruments are like the ultimate space laboratory. Some can even take high-contrast images, blocking out the blinding light of a star to directly see a planet or disk of material around it. Each instrument is managed by its own set of computers, loaded with specialized software that sifts through the torrent of incoming data, spotting real astronomical signals and tossing out almost all noise. Getting all these systems into space safely required a rocket and a launch sequence that was, plain and simple, one of the most stressful space moments in decades. Webb's folded-up design was jammed into the nose cone of an Ariane 5 rocket, but launching was just step one. In the weeks after launch, everything had to unfold: mirror segments, the sun shield, smaller secondary mirrors, antennas, radiators, sometimes in sequences that took hours or even days, each step controlled by teams on the ground, sending carefully timed commands. If anything had jammed or drifted out of place, it could have spelled disaster, but every piece locked into position, paving the way for the mission to reach full focus. After deployment, aligning the mirror was another technical feat. For the telescope to be razor sharp, each mirror segment had to be nudged, checked, and fine-tuned so their reflections all lined up perfectly, producing a single focused image. Powerful lasers, cameras, and algorithms worked together day and night, sometimes moving mirrors by less than 1,000th of a millimeter at a time, gradually improving the image until James Webb saw as clearly as it was designed to. Positioning James Webb at the Lagrange point L2 has huge benefits. Here, the observatory can stay pointed at targets for days or even weeks, without the constant motion and bright light interruptions that affect telescopes closer to Earth. This is crucial. Detecting the transit of an exoplanet like XZ13b, meaning seeing the tiny drop in starlight as the planet passes across its star, requires watching the same star for a long period. Even the tiniest atmospheric changes have to be measured, so it helps if the telescope isn't jostled by Earth's gravity, air currents, or sunlight. The observatory also needed a way to handle huge amounts of science data. Every time James Webb takes a picture or records a spectrum, it generates files that can be dozens, hundreds, or thousands of times bigger than a typical smartphone picture. That means onboard computers are constantly sorting, compressing, and checking data before sending it back to Earth through powerful antenna systems. On Earth, this data flows into a whole pipeline of servers, researchers, and automated programs that check for errors, clean up cosmic ray hits, and get the information ready for scientists everywhere to study. Another piece of the puzzle is how James Webb avoids false signals. Space is a noisy place, full of cosmic rays, charged dust, and hardware glitches. The engineering teams created complex software systems to compare multiple exposures, remove bad pixels, and stack short images into a high-contrast view. Special calibration procedures are carried out before and after each important measurement to check for drift, temperature changes, or electronic static. Teams run data simulations to make sure unexpected signals really come from space, not from the telescope itself. When it comes to looking at exoplanets, precision is everything. Webb's spectrographs are tuned to pick up the faint traces of starlight shining through a planet's atmosphere during transit. It can identify dips of only a few parts per million in the star's brightness, far smaller changes than astronomers could ever see with Earth-based telescopes. Being able to tell apart a spectrum with a little more methane or a little more water vapor means Webb had to eliminate interference from its own electronics, from shifting temperatures, and even from sunlight reflected off tiny particles in space. That's why temperature stability, computer controls, and precise movement of each lens and mirror are so non-negotiable. Keeping a telescope the size of a house stable for days on end while rotating it to new targets is handled by high-precision gyroscopes and reaction wheels. These allow James Webb to stay locked in on a spot in the sky to a precision of just a few milliseconds, a technical way of saying it doesn't drift or wobble. The pointing system is even equipped with fine guidance sensors, which use selected guide stars to maintain the aim of the telescope. When scientists target places like XZ13b, these systems make sure every frame stacks up exactly, and every transit event is measured without blurring or distortion. Routine maintenance and remote updates are built right into the software. Whenever the engineering team finds a new way to sharpen images, weed out glitches, or boost efficiency, they simply upload patches and checkups over the network, just like updating an app on your phone, except the phone is a 1.5 million kilometer distant science laboratory with absolutely no room for mistakes. Webb's detectors, unlike many older telescopes, don't just do one thing at a time. The mission team can schedule multiple overlapping observations, maximizing scientific return. While the main camera points at a particularly interesting target, other instruments might be doing quick scans of background galaxies or even measuring cosmic background radiation. All the data gets tagged, time-stamped, and prioritized for downlink, helping the team keep up with the mountain of information flowing in every day. Because the telescope is so sensitive to heat and light, it was important to design ways of protecting it from anything that might cause a spike in temperature or a sudden burst of energy. That means careful planning for what parts of the sky to look at during each season, and regular checks to make sure no motors, heaters, or electronics run at the wrong time. Anything that could shift the temperature even a tiny amount gets flagged and monitored, so the science doesn't get thrown off by a quirk in the machinery. Launching and operating James Webb was so complicated that dozens of agencies had to work together. NASA led the charge, but the European Space Agency, the Canadian Space Agency, and contractors and specialists from across the globe all played key roles. This meant coordinated schedules, standard codes for hardware and software, and agreements for sharing and analyzing massive amounts of data. Every time Webb turns to a new exoplanet or distant galaxy, it is drawing on the skills and planning of engineers and scientists from at least a dozen countries. Once in space, James Webb's real power comes from its ability to spend long periods watching faint objects. When it targets a planet like XZ XZ13b, it can spend hours or even days collecting photons. That means building up the kind of signal that scientists need to detect tiny changes as an exoplanet passes through its star's light. This is what lets them separate the different gases in the planet's atmosphere and look for clues that something alive might be present. The longer the telescope stares, the better the data gets, reaching a level of detail that would have been impossible just a few years ago. Every image and spectrum taken with the telescope is checked and double-checked by teams across the world. Any sign of an unusual feature, be it a dip in starlight, a funny shape in the spectrum, or a repeatable pattern matching theoretical models, gets flagged, discussed, and analysed in painstaking detail. Computer simulations, error modelling, and reviews by independent panels are all standard, helping to ensure that what comes out of Webb's data is real and reliable. When you step back and think about what James Webb can do, it's clear that every tiny detail in its design helps scientists get closer to truly answering whether life exists beyond Earth. The mirror's gold coating, the huge and intricate sunshield, the ice-cold detectors, the pinpoint pointing systems, the long-distance communications, and the non-stop international teamwork, it all had to work perfectly, and it does, letting the telescope achieve the kind of sensitivity and accuracy that makes discovering planets like XZ13b and analysing their potential for life actually possible. Thanks to all these advances, Webb is more than just a single leap forward. Every exoplanet discovery, every confirmation of water, methane, or oxygen, and every refined chemical fingerprint is a direct result of tackling and solving thousands of engineering and operational hurdles that had never been overcome before. The technology, planning, and cooperation behind Webb aren't just about building a machine, they're about giving humanity the tools to find out just how big and complex the universe really is. That's what makes each finding so remarkable, not just what is discovered, but how it was made possible in the first place. All this cutting-edge engineering and scientific coordination has brought us right to the threshold of what comes next for a planet as intriguing as XZ13b. With huge investments, incredible teamwork, and years of technological progress already paying off, researchers around the world are locking in on a common question. Now that we have such promising results from the James Webb Space Telescope, how do we move forward to study XZ13b in greater detail? This is when the focus shifts from the result of almost certain life to the much larger effort of observation, verification, and planning for deeper exploration. The first thing on everyone's mind is scheduling more observing time with James Webb itself. Each time the planet passes in front of its star, a transit, the telescope has another shot at gathering high-precision atmospheric data. These opportunities come at intervals set by the planet's orbital period, which, for XZ13b, might be anywhere from a few weeks to a few Earth months depending on the exact layout of its solar system. Each transit is critical, giving the chance to collect more light, improve the signal-to-noise ratio, and catch seasonal or weather-driven variations in the planet's atmosphere. The more transits observed, the more scientists can tell if those intriguing biosignature gases are steady or if they change over time. But Webb's schedule is jammed. There's a long list of teams wanting a piece of its observing time for every imaginable cosmic target, from the earliest galaxies to new exoplanet finds. Getting repeat observations of just one exoplanet requires approvals, computer modeling, coordination, and sometimes waiting for parts of the telescope schedule to open up. When XZ13b made headlines, researchers quickly filed target of opportunity proposals. These are requests to give this planet priority because of the exceptional stakes. Each new round of data is analysed by multiple groups, often with independent methods, to try to catch every possible clue and avoid mistakes. No one wants to miss an unusual pattern or explainable chemical process. Researchers are also keen to obtain new types of data to complement what Webb is getting in the infrared. Ground-based observatories on Earth are being recruited to monitor the host star for activity, like flares, spots, or cycles that might mess with the apparent chemical makeup of the planet's atmosphere. Using radio telescopes and optical telescopes, astronomers can double-check that no weird magnetic or brightness events are skewing the data. A planet's star is just as important to study as the planet itself, especially when subtle signals could be faked by changes in the star's normal behavior. Another approach is to use other instruments in space. The Hubble Space Telescope, which sees mostly in the ultraviolet and visible light, is sometimes also pointed at the XZ13b system to hunt for different atmospheric components, like ozone or other molecules that Webb might miss. Newer satellites, like the Transiting Exoplanet Survey satellite, can help by refining the planet's orbit, confirming its size, and ruling out false positives, other objects mistaken for planets, for instance. All these different datasets come together to build a clearer, multi-wavelength picture of both the star and the planet. There's a lot of excitement and some real strategy in planning future missions that can go above and beyond even what Webb can do. Several big projects are on the drawing board or moving through early development. The Habitable Worlds Observatory is a telescope designed to look for Earth-like planets and directly image their surfaces and atmospheres, possibly with even higher sensitivity than Webb. Another project, LUVOIR, aims to be a powerful, multi-purpose observatory that could take direct images of exoplanets by blocking out their host star's light with a built-in coronagraph. The kind of images and data these future telescopes could provide would be next level, mapping clouds, seeing continents or oceans, and possibly even catching glimpses of seasonal changes that go with plant growth, storms, or shifts in climate. Getting funding and final design approval for these missions depends a lot on the discoveries being made right now. James Webb isn't only about direct observation either. Its data is being used to fine-tune computer models and simulations that help narrow down what we should be looking for next. By feeding every new measurement into these models, researchers can predict the best wavelengths for future observations, test out new hypotheses about the planet's interior and atmosphere, and design instruments that would maximize the chance of picking up subtle, unusual signs. This is especially important for finding things like unstable molecules, rare elements, or patterns that might show up only during storms or planetary seasons. Astrobiologists are hard at work debating and expanding the list of possible biosignatures to check for on XZ13b. On Earth, life produces gases like oxygen, methane, and nitrous oxide, but it's hard to know exactly what would count as clear evidence on an alien planet. The more Webb watches, the more complex the picture gets. Life elsewhere might use chemistry that is totally new to us. Remote sensing teams are also hunting for technosignatures, artificial signals like weird radio bursts, non-natural chemicals, or possible signs of technology. Most researchers still expect microbial or plant-like life to be the first discovery, but no possibility is left out of consideration. One major challenge on everyone's mind is separating genuine life from unknown or poorly understood geology, chemistry, or atmospheric physics. Teams around the world are constantly updating laboratory experiments, running chemical simulations, and comparing what we see on Earth and in space with new data from Webb and other missions. The point is to really pressure test every possible non-biological explanation, so if life does get confirmed, the evidence is as solid as possible. Nothing is more disappointing for the scientific world than a false alarm, so they're cautious at every step. International collaboration is becoming even more important now. Space agencies from North America, Europe, Asia, and South America are sharing raw data and discussing plans to coordinate observations. The more tools and eyes watching XZ13b, the better chance there is of finding something new or explaining away any anomalies that might show up. Data is being made available to researchers in real time, letting independent groups check and challenge each result. Science is best when nothing gets rubber-stamped and skepticism remains high. A growing part of the plan is public outreach. People everywhere want to follow the XZ13b story, understand what's going on, and see the search unfold. Agencies are setting up open data portals, publishing online resources, and streaming live telescope events when new data comes in. Educators and science writers are turning each round of findings into lessons, explainer videos, and interactive tools for classrooms. This keeps society engaged and helps maintain support for long-term research, both in terms of funding and popular interest. Some teams have started to get creative about what else could be learned from the XZ13b system. For example, looking for changes in the planet's thermal emissions over time might hint at volcanoes, continental drift, or massive storms. Any variability in reflected light across the orbit could mean surface features, oceans, deserts, or ice caps are shifting. The data might even show hints of auroras, dust storms, or active chemical cycles nobody predicted. Every good idea is being tested. and the community is open to publishing both positive results and negative searches in case someone else can catch patterns others miss. In the meantime, astronomers are compiling detailed theories about how XZ13b came to be. Modeling the formation of its star and planet helps answer questions about the origins of its odd chemistry, atmospheric structure, and possible climate history. By comparing its properties to other systems, scientists might also notice trends or unique signatures, which can then be applied to the search for other promising planets. As for direct exploration, no technology available today is ready to send probes, let alone humans, to a star system more than 100 light-years away. But the planning has already started. Ideas for robotic interstellar precursor missions are under review by various space agencies. These would use technologies like laser-powered light sails or next-generation ion engines to send small, lightweight craft toward nearby stars, including XZ13b's system. Even if travel times are measured in decades or centuries, the first steps, testing propulsion, miniaturizing instruments, and sending prototypes to the outer reaches of our solar system, are getting funded and designed now. While waiting for that, huge advances in artificial intelligence, data analysis, and imaging software are making it possible to squeeze much more information out of the images and spectra that are already being collected. Research teams are training algorithms to pull out subtle, repeating signals that might escape the naked eye, to simulate the look of a distant planet's weather system, or to spot tiny outliers that point to new chemistry or even the unlikely possibility of technology. Another part of the future plan is to build all the knowledge gained from XZ13b into better searches elsewhere. Every new confirmed biosignature sets a benchmark. We now know what to look for, how to model it, and which instruments work best for the job. Catalogues of exoplanet fingerprints are growing, letting teams sort through thousands of candidates for worlds that best match XZ13b's winning formula. This pushes the whole field forward and helps make sure new discoveries are not missed. Preparation for the psychological and communication side of things is underway as well. Agencies know that a huge scientific claim, like finding life for certain, carries big responsibilities. Experts on communication, ethics, and risk are already drawing up plans for how to present new evidence, respond to skepticism, and keep everything transparent if dramatic updates arrive. Outreach efforts make sure the public stays informed and included, especially because these discoveries have the power to change how people everywhere feel about their place in the universe. The ripple effect on other science fields is growing too. Chemistry, geology, biology, computer science, and even engineering are all being pulled into cross-disciplinary projects that focus on life detection. University programs are offering new courses, sending students into labs to help design and run experiments that model possible environments for XZ13b. Every bit of learning from other fields is eventually folded back into the telescope and lab work that is the bedrock of discovery. Even amateur astronomers and citizen scientists have a seat at the table now. With so many light curves and so much data, some programs let non-experts help scan for transit signals, check for oddities, or track changes in the host star's brightness. Crowdsourced projects have already flagged exoplanet discoveries before, and including these outside eyes makes it more likely new developments will pop up sooner rather than later. The immense flow of fresh data and the growing possibility of complex life or even biosignatures will mean years and years of follow-up. That's the essence of the scientific method. Repeat the tests, rule out mistakes, and only announce truly extraordinary results when there's no reasonable doubt left. XZ13b will stay at the front of every scheduling and planning meeting, with on-call teams ready to adjust Webb's targets or call in new missions when updates to the evidence demand it. As each new observation comes in, the results might push scientists to ask more and more specific questions. Does the planet have a strong magnetic field, protecting its air and perhaps hinting at an iron core? Are there smaller companion planets in the system that could affect its stability, climate, or water supply? Could giant impacts, moons, or asteroid belts play a role in shaping its environment, like they have in our own solar system? Every new clue spins off into new lines of research, feeding back into the big story. There's also a move to monitor the broader cosmic neighborhood of XZ13b. Its star, nearby stars, and any other planets or debris are tracked to build up a full dynamic picture of what's happening there. The context can matter as much as any single measurement, especially when trying to rule out rare events or background effects that could mislead everyone about the real state of XZ13b's habitability. Even with all these plans, the big wildcard is what we might find that nobody has even thought to expect. Over the coming years, unexpected patterns, wobbles, or chemical mismatches could suggest either a totally new category of life or maybe something even more surprising. That is why all the teams involved are so careful to be ready for whatever the universe decides to reveal next. The unique opportunity that XZ13b offers is actually shaping the wider field of astronomy and science. Every time new data narrows the possibilities or confirms a big prediction, funding agencies and research groups everywhere gain momentum to request more missions, better equipment, and more creativity. The legacy of this planet will be not just what is learned about one place, but how it stretches the world's imagination for what can be found in the stars. So, as the buzz around XZ13b continues to grow, the next steps are clear. It demands patience, constant double-checking, worldwide sharing of ideas, and above all, the determination to keep exploring with every tool available. The global focus on this single planet means discoveries that will likely echo across many fields of study for years to come, changing the way people look for life, design technology, and work together on the search for other worlds like our own. With all the effort and new strategies focused on XZ13b, there's a natural shift happening in the world of astronomy and planetary science. Every observation, new plan for better instruments, and cycle of shared data is expanding the possibilities for where we look for life. The broader picture is much larger than a single planet, no matter how promising XZ13b is. Once a candidate comes along with a 96.8% likelihood of habitability, that sets off a change in how researchers view not just one world, but the odds across the entire galaxy. The way scientists and even regular people talk about habitable planets and exoplanets all over the universe is fundamentally different now. Back before telescopes like the James Webb, astronomers mostly guessed at the odds for life elsewhere. The main way to make those guesses was to look at our own solar system, compare a few details about planets and moons, and hope for the best as distant planets turned up in surveys. Most of the exoplanets found in the 1990s and 2000s were huge, hot Jupiters with orbits close to their stars, or frozen gas giants far out. Very few were both rocky and sitting in the sort of Goldilocks zone where temperatures are nice enough for liquid water. That's a key, since just having a planet, or even thousands of planets, doesn't mean much if they all turn out to be inhospitable gas balls or scorched pebbles. But as the years went by, new surveys from telescopes on the ground and in space started filling in gaps. Missions like Kepler changed the numbers completely. Astronomers learned that planets around other stars are not rare exceptions, they're the rule. It went from wondering if there are a few hundred planets out there to knowing there are more planets than stars in our galaxy, numbering in the hundreds of billions. Still, the tough part was filtering that enormous pile of worlds to find the kinds actually worth calling potentially habitable. Kepler and later TESS were great at flagging planets that cross in front of their stars, letting us estimate their size and orbit, but they could only guess at the details of the atmospheres. So the chances of finding a planet that looks a lot like Earth always seemed uncertain based on limited evidence. When something like XZ13b appears, things start feeling very different. Suddenly, a telescope actually detects the combination of gases, surface temperatures, and long-term stability that fall exactly into the sweet spot for biology as we know it. That means every rocky exoplanet candidate with a similar orbit or similar star profile immediately becomes more interesting, not just science fiction, but possible science fact. If it can happen once, then statistically, it can probably happen again and again, given the sheer number of chances available in our galaxy. This is a huge turning point for the overall search. Astronomers are now able to take the data from Webb, Hubble, TESS, and all the supporting ground-based studies to put together better models of habitability. These models no longer guess wildly about life's odds. They actually use measured fingerprints from places like XZ13b. Computer simulations adjust the filters that look for water, methane, or oxygen, so when new exoplanets are catalogued, their profiles can be graded for promise. Whole new categories have emerged: super-Earths, mini-Neptunes with thin enough atmospheres to be stripped to rocks, ocean planets, desert worlds, and more. Some teams are building up libraries of comparison spectra, so a future planet with even a faint resemblance to XZ13b can instantly rise to the top of observation lists. Having a strong candidate with so much evidence for habitability finally shifts the way funding and resources are allocated. Science agencies and universities are more confident to request telescope time, computer resources, and even laboratory experiments to chase down the most promising targets. The bar for what gets called a habitable candidate is much higher now. It's not just about being the right distance from a star, but about delivering actual, measured atmospheric chemistry and evidence of climate cycles. Groups working on missions for the next couple of decades will use XZ13b as a matchstick to test ideas, instrument design, and even risk calculations for future telescopes, especially those that might try to image surfaces or capture time-lapse data to spot changing features. This new focus isn't just about planets exactly like Earth either. If XZ13b proves there's life on a super-Earth or on a planet with a slightly thicker atmosphere, then the search can include more exotic candidates, rocky planets with a little extra mass, orbiting stable, sun-like stars, or even cooler red dwarfs will get prioritized. Planets with clear weather signals or evidence for magnetic fields will matter much more. That makes the overall pool of potential targets much broader, because even if conditions are a little different from ours, there is now solid reason to think that life could find a way in more places than first assumed. Patterns are another big breakthrough. The more exoplanets are put through close analysis like XZ13b, the better scientists can spot trends, like what types of stars produce the most promising planets, or whether certain chemical combinations show up repeatedly. With each new observation, astronomers can build up statistics. Maybe 10 out of 100 seemingly habitable planets check every box, or just 1 out of 1,000 does. These numbers have real power because they help answer that core question that's been hanging over this whole field for decades. Is life rare, a lucky fluke, or is it a likely outcome when you have the right ingredients and enough time? In the years since telescopes started turning up hundreds, then thousands, then tens of thousands of candidate planets, the exoplanet science world has matured fast. Teams are now split into two big groups. Some are focused on finding every last possible exoplanet, no matter how weird. Others specialize in sorting through that huge pile to pick out the ones most likely to resemble XZ13b. This approach is getting more efficient all the time, thanks to machine learning and better computer models, but it also relies on the patient build-up of shared databases, cross-checked results, and international teamwork. People might ask if news about a planet like XZ13b means intelligent life, civilizations, or anything as dramatic as what's seen on television or in movies. The answer is that the new situation mostly improves odds for simple biospheres: plants, algae, bacteria, things that alter their environment in measurable ways. But as the research community gets better at finding places with chemistry out of balance, the next logical step is to look for complexity. That means watching for evidence of seasonal cycles, planetary weather, or gases that stay in the right proportions only when there is some ongoing renewal process, a classic hallmark of biology. These changes to the strategy are also making the search for life less Earth-centric. One important lesson from XZ13b is not to make the definition of habitability too narrow. Planets that seem a bit too big, a tad closer or farther from their sun, or with slightly odd chemical signs might now deserve a second look. Unexpected possibilities, worlds with thick clouds, strange oceans, or alternate geologies get more attention when scientists realize that one or more biosignature gases could form in a variety of settings. Instead of discarding candidates that don't fit the textbook Earth model, teams try to model every possible twist of climate and chemistry using XZ13b's unique signatures as one way to bridge those gaps. This broadening of the search has practical effects. More exoplanets are flagged for careful monitoring, and new ground-based and space-based telescopes are being designed specifically to home in on the best candidates as soon as they're found. Missions like Ariel, JWST themselves, and others set for launch in the 2030s will prioritize not just masses and orbit zones, but full atmospheric scans. Projects to directly image exoplanets are now seen as vital because a proven living planet makes the case for investing in the advanced optics, coronagraphs, or star shades needed for real planet portraits rather than faint, indirect signals. The entire discovery pipeline is getting faster. When a world appears with even faint signs of an interesting atmosphere, observation time is hastily scheduled, proposals move to the top of the stack, and teams worldwide pore over the new data. Anyone who thinks of a new way to cross-check or verify the findings can quickly share their results. In some ways, the search is now more open than ever, where a new discovery on one planet instantly reverberates across the entire research world, triggering a new wave of ideas for instruments, missions, and observation plans. There are trickle-down effects for other scientific fields too. Geologists create experiments in the lab to mimic strange atmospheres or planetary surfaces. Chemists search for the kinds of reactions that could replicate the biosignature chemistry seen remotely. Biologists try to imagine the full range of evolution that could take off in non-Earth settings. Even social sciences are watching how news about possible alien life travels online, and how culture, funding, and community excitement all feed back into what gets researched next. Education and outreach are also being reshaped. Now that the public is hearing about Earth-like or biologically active planets in the news, there's more demand for plain language explanations. Museums, science centers, and online education platforms jump in to keep people updated as the field moves quickly. Kids who might have overlooked astronomy in the past are now interested in planetary science and exobiology, the search for life elsewhere. Another big consequence is for government funding agencies. It's much easier to argue for huge budgets and long-term telescope proposals when there's hard evidence that planets like XE13b are not rare one-offs. The more planets are discovered that hit every major habitability metric, the more support is available for new launches, data processing power, and international partnerships to move the science even further. Whole new projects spring up to answer lingering questions. Is there typically just one habitable planet per star? Do biosignatures tend to occur in clusters, hinting at special neighborhoods or star-forming regions with good odds for life? How do planets that seem like twins actually turn out to have big differences when seen in detail? Each confirmed planet with a strong biosignature becomes a touchstone for models that will reshape theories about planet formation, star evolution, and the chemistry of life itself. It's not just about looking at the current generation of telescopes either. Planning for bold missions, interstellar precursors, next-generation space arrays, orbiters with high-resolution cameras, or even eventual probe launches gets justified by each new breakthrough. XZ13b and its siblings help testers and designers create hardware that will last, gather faint light with better accuracy, withstand years of radiation, and send back information from across unimaginable distances. Even science fiction and philosophy are catching up to reality. Writers, ethicists, and artists suddenly have more real-world material to draw on, replacing guesswork with data and blurring the lines between what if and what is. Some of these conversations touch on how to handle contact, who speaks for Earth, or what it means when news about life elsewhere becomes part of day-to-day reality. The change in how discoveries are evaluated means the field is less about lucky breakthroughs and more about a steady, relentless push toward mapping the actual diversity of planets in the universe. If a planet as promising as XZ13b can pop up with strong signals, everyone knows there are surely more waiting to be noticed or understood. Statistically, if there are 100 billion stars, and even a fraction of them hold promising planets, the odds for finding more cases of life, or at least more candidates, keep rising. With every similar detection, researchers look for patterns. Are there habitable zones in star clusters or molecular clouds, or is the process totally random? Do planets orbiting red dwarfs really get bombarded by radiation, or have we underestimated their ability to keep stable, life-supporting climates? These are the angles that get more attention now that solid biosignature detections exist. The practical aspect is that having good evidence changes what gets built and what questions are considered. As methods improve, unexpected kinds of life or biosignature patterns could come to light. New telescopes and sensors that might have been shelved for lack of urgency are pushed back into development because they can help chase that kind of discovery on a wider scale. Every detection, even if it's just a strong maybe instead of a guaranteed hit, snowballs into more ambition for astronomers and a bigger network of people interested in exoplanet research in general. Schools schools, universities, and even governments start using the new findings to inspire students, strengthen STEM fields, and keep space programs in the public eye for longer stretches. So, the stunning findings from XZ13b aren't just about that one world. They change the way people look for life everywhere. They help define a new era in exoplanet science, where confirming a living planet is not a dream, but an ongoing challenge and a realistic goal. Every new planet discovered and confirmed is a new puzzle piece in the map of our galaxy and a reminder that the search is just beginning. All these discoveries, expanded research methods, and shifting perspectives in the field have brought us to a totally new moment in human history. Right now, science stands in a place that people only dreamed about for centuries. With confirmation of a planet like XZ13b, one with real, consistent evidence pointing toward a very high probability of life, everything about how we see ourselves and our goals as a species takes a fresh turn. It is no longer just about cataloguing stars or learning how galaxies form. It is now about figuring out what it means for humanity to be part of a far larger web of living worlds. To start with, having solid evidence that life exists or has existed elsewhere in the universe changes the big picture for almost every field, and it puts the story of Earth into cosmic perspective. Instead of wondering if we are the unique exception, we now see that Earth is likely one among many places where biology has managed to take hold. This means the dreams and guesses of scientists, writers, and everyday people have come up against actual, testable reality. How Earth fits into the universe is becoming a scientific question, not just a matter for stories or hope. The drive to keep exploring will only get more intense. With just one planet showing this high likelihood for life, it's nearly guaranteed that funding and energy will pour into building telescopes and sending missions with greater reach. Space agencies will expand their plans, and space science teams will draft new roadmaps for finding not just life elsewhere, but different types of life. Perhaps some like us, maybe some totally unfamiliar. Questions about how life arises, spreads, or adapts now have new urgency. The more we learn, the more we realize that we are only at the start of a huge science journey. For governments, this changes long-term strategies. Interest in planetary protection, everything from keeping our own planet safe to being careful about what we send to other places, increases. Existing rules about exploring Mars or Europa are already strict, but with evidence for distant life, these discussions will grow much wider. International rules could start covering not just planets in our solar system, but worlds far beyond, focusing on respect, cooperation, and maybe even ways to avoid contaminating alien biospheres or bringing anything dangerous back home. Science and political priorities get realigned almost overnight. Space is no longer just about satellites, GPS, and climate monitoring. It becomes a shared frontier, where the main goal is no longer simply observation, but building new connections and understanding. Countries and agencies that were once mostly racing to be the first may put more effort into collaboration, since everyone realizes that discoveries of this scale impact the entire world, not just one group or nation. Funding organizations will invest more not only in astronomy, but also in education and technology development, trying to attract the new generation of scientists, engineers, and thinkers who want to study life beyond Earth. School and university programs will rush to update. Courses on astronomy, biology, chemistry, planetary science, and computer modeling will see new students, some of whom are motivated directly by the recent events in exoplanet science. Graduate projects, summer programs, and even primary school teaching materials will include research about XZ13b and the hunt for other living planets. Libraries, museums, and science festivals will update exhibits and materials, focusing on this era as the moment we realized life is not just a local phenomenon. This isn't limited to education and pure science. Technology itself will get a boost, building the instruments to spot, analyze, and one day, maybe even visit these planets requires even better optics, faster computers, stronger robots, and bigger or longer-lasting space vehicles. Robotics companies, artificial intelligence firms, observatories, and sensor designers now find themselves pulled into solving the new challenges of planet hunting and biosignature verification. With real-life examples instead of only theory, these technologies will grow faster and likely spill over into other sectors, benefiting Earth in unexpected ways. The private sector can't help but join in. Satellite companies, new space startups, and data science firms will want a piece of the action, offering everything from light-collecting hardware to cloud-based platforms for analyzing astronomical data, investors may support the next generation of research satellites, private ground stations, or even the wild dream of sending commercial robotic probes on the first steps toward interstellar journeys. Public excitement and sense of possibility tend to make risky investments a little easier to justify. Wider society, too, will keep feeling the impact. Popular culture already rushes to incorporate the science, with new movies, television series, games, books, and podcasts exploring what it means to find life elsewhere. Artists and musicians might create new works inspired by XZ13b or its imagined life forms. Fiction and storytelling will branch out, using the reality of near-certain alien life as a premise, no longer as pure fantasy. Big questions will keep arising and will get more specific as time goes on. News will report on each update, from small refinements in atmospheric chemistry to plans for a future probe, or even just a new telescope proposal. Some outlets will focus on the practical side: technology, missions, risks, and the technical challenges of the search. Others will run with the philosophical, ethical, and sometimes even speculative debates. These stories will reach every corner of the world, filtering into all languages, communities, and cultural traditions. For ordinary people, conversations at dinner tables, in classrooms, online forums, and workplaces will often come back to the same themes. Some will be fascinated and want to know all the details of each new mission. Others may wonder about the risks and responsibilities that come with searching for, or even making contact with, new forms of life. There will be interest in how scientists check their findings, how agencies share information, and whether we might ever cross the gap to actually visit planets like XZ13b. The new era will bring some practical shifts in thinking about Earth itself. When we realize we are not the only living world, it makes protecting what we have feel more important. Maybe there will be more urgency around climate action or respect for biodiversity, as Earth is no longer special in its living status, but unique in its details, its story, and its people. Environmental movements might use these discoveries to argue for even greater protection of Earth's ecosystems and clearer international cooperation for the good of present and future generations. In the long run, the biggest shift may simply be in confidence and sense of possibility. Through most of the last century, astronomers hoped but never knew for sure if the search for life elsewhere would pay off. Now, the evidence is tipping, and the decades ahead feel less like a guessing game and more like a systematic exploration, one where patience, rigor, and creative thinking really can pay off with historic results. Every new detection, every step forward will be reported, debated, and built upon. And with more planets joining the list of promising discoveries, the momentum will keep building. Thinking about the next 50 or 100 years, you can imagine powerful new telescopes, space-based, ground-based, or maybe both, working together to map out the atmospheres of thousands of habitable planets. Instruments might detect not just the signs of simple life, but complex biospheres. Perhaps robotic spacecraft will, in the far future, be sent to nearby promising systems using next-generation engines or light sails, delivering back data that lets us study alien climates up close. Communication efforts, both scientific and public, will remain a high priority. Transparency about data, about what we know and do not know, and how findings are confirmed, will build trust. The lessons learned from past false alarms will keep science cautious, but each confirmed fact will reinforce the sense that the universe is not empty, but filled with places where life can take root. The discoveries will ripple outward into economics, education, psychology, and even ethics, as people adjust to a reality that is genuinely bigger than anyone used to think. Some will still hold back, whether for personal, philosophical, or religious reasons. But for many, the discoveries will open up more curiosity and questions, not just about other planets, but about the trajectory of humanity itself. It's also possible that over time, expectations will change. What now seems like a massive leap may eventually be seen as a natural step, as more data and more habitable worlds are added to the catalogue. Just as people eventually got used to flying across continents or communicating instantly with anyone on Earth, the idea of living worlds across the galaxy may move from incredible surprise to everyday background knowledge in just a generation or two. Already, textbooks and science communication are shifting to include the latest finds, turning what would once have been mind-blowing news into the foundation for more research and more ambitious plans. What stays unchanged is that awe and excitement keep people, and especially the youngest scientists, asking the kinds of questions that push discovery further. Why does life begin? How does it survive? What does it look like somewhere else? And, with every new chapter, are we ready for whatever we find? In a very real sense, the era that begins with XZ13b is shaped by a new perspective, Earth as one among many. That makes humanity smaller, maybe, but also part of a much bigger universe. Work will continue, telescopes will scan the skies, and every planet, moon, or signal brings a piece of the puzzle closer to being solved. For every headline and every big mission, there will be thousands of hours of careful observation, debate, checking, and sharing. The excitement and energy that come from this discovery will be a driving force, setting up generations to ask more questions and maybe, one day, to go see what's out there in person. The future is open and full of possibilities. Space agencies and researchers will draw on both what we know now and what we keep discovering, always building on a foundation that grows wider every year. With each confirmed world, each new discovery, and each breakthrough in technology, humanity's place in the cosmos feels just a little bit more connected, tied not just to this planet, but to a galaxy rich with potential for life. The James Webb Space Telescope and everything that comes after it will be the tools, but it's really about curiosity and teamwork. Those are what move the boundaries of knowledge forward, and that is how this new chapter in the human story will be written.